Hi everyone, my name's Morton. Today I'm going to talk about some of the lesser known features in Cassandra 2.1. Now, I started using Cassandra at version 0.4, and there are a lot of great features in 2.1. Help with performance and availability and usability, and if we tried to go through them all, we'd be here all day. So instead, we're going to talk about the things that have appeared over the last year, sort of in version 2.0 and 2.1. A little bit about myself before we start. I'm the co-founder of a small consultancy called The Last Pickle. We work with clients to deliver and improve Apache Cassandra-based solutions. I live in Wellington in New Zealand, and the rest of the company's in the United States. We're going to look at configuration changes, a couple of things that are handy in CQL3, some information about new tooling, and then some of the internal changes. The easiest thing to start with in configuration is that we've replaced log4j with Logback. And if you look at the ticket for this, Cassandra 5883, you'll see it says that Logback is faster and it has better auto-reloading. And it has this nice feature where it can automatically archive the log files as it rolls them around. We'll see that in a minute. And there's a new configuration file, logback.xml. Now, even though this is XML, it is still a lot better than the log4j configuration file. And that's just because log4j was so bad. So that file looks like this. There's a couple of important points here. The location of the system.log is set by looking at this system property called Cassandra.logdir. Now we're going to have a look at that in a minute, see where that comes from. And the second section in red there explains the policy for rotating the files and the archive policy. So with the .zip there, it will automatically zip those files up. And the last thing I want to point out is how you set the logger log levels. This is so much better than log4j. It makes clear sense about what you're actually doing. One tip that I have is that if you're using this, change the path for that auto archive to be a .gz rather than .zip. When you do that, zless and zgrep will work over those zip files, and they'll also work over the non-archived files, and your life will be a lot easier. So if you run this in production now, your log directory may look like this. You have one log file and the other's a .gz. That can make it a bit easier to copy them around because they're normally 20 meg files. Now, the next thing we have are some command line parameters. These are passed into the JVM when we start it up. The code reads them and adjusts its behavior in some fashion. We have a couple of new ones, Cassandra.logdir and Cassandra.storagedir. These are part of ticket 7136, and this is where we set new default paths for the log and for the data and for the commit logs. Now these default paths only apply if there's nothing set in Cassandra YAML. The package installs actually reach into the YAML file and set those paths. So if you do a package install, nothing changes. If you want to have the new defaults, which place these things under the parent of where Cassandra is run from, then you leave the YAML file clear. And that's what it is in the code base now. If you're running the tarball, you'll see this. Inside your Cassandra v 2.1 directory, there's a new directory that will get created when you start, called data, and another one for logs. Inside data, you'll find commit logs, save caches, and data. Now, this is kind of handy when you're just mucking around. If you've been using Cassandra for a while in your company, you may end up with a directory like this on your machine, where you have every different version of Cassandra that you have to be concerned with, and it's now awesome that all of the data and logs and lives under those directories with the config. There's a couple of extension points now. Cassandra config.dir allows you to specify the class path for a class that implements this interface config.configurationLoader, and that allows you to get into the process of configuring Cassandra. The configuration loader is responsible for reading the YAML file and reconstituting that into an object called config, which is then validated and put into an internal object called the database descriptor, which was where all the configs read from. So you can get into there and override the configuration. That can be useful if you're embedding Cassandra inside your test environment, or you're just embedding it in a service, and now you can put you can control that config programmatically. It's also useful if you want to put the config somewhere else. You don't want it in YAML, you want it in Zookeeper, for example. There's another extension point, Cassandra.custom_QueryHandler class. This allows you to specify a class, again, implements an interface called CQL3 QueryHandler, and allows you to get in between every CQL3 call that comes into the server. So if you wanted to do some extra logging specific to your organization, or you wanted to have your own brand of slow query log, you can do that. If you wanted to actually stub out all of Cassandra, for example, you're testing a new driver, you can do that. You can just hop in there. You don't have to call the database. You can just return foo all day long. That interface looks sort of like you'd expect. There's calls on there to process queries, prepare queries, process prepared queries, that sort of thing. Now, this was a patch that came in early in 2.0, around 2.02, and it's awesome. Have a look at this GitHub project. When you specify a file to Cassandra.metrics_reporter config, we will parse that and create some Yammer metrics reporter agents. These run inside the JVM that Cassandra's running in, and they can be configured to automatically push metrics out. There's reporters for Graphite and Ganglia and Riemann, and I'm sure you can go and write any others if you're using different things. You should be using this. It's awesome to just constantly have Cassandra always pushing 1 second metrics over to Riemann every time you start Cassandra on your computer. And we do this with, this is what that configuration file looks like. If you're doing it for other ones, you should have a look at that GitHub project. But you can go in there and say, hey, here's a regex, go and dump all of these things out to this port. Cassandra 4.8.09 adds a neat little trick if you ever find yourself in trouble. And it's always handy to know what are the features that are going to help me when I need them the most. The replay list parameter allows you to specify a comma-separated list of key space and table name. And when we replay the commit log, we will only replay mutations that apply to those tables that you specified. Of course, if you don't specify anything, we'll replay all of them. If you find yourself in a situation where you are doing point-in-time recovery, so you've perhaps used the commit log archiving features, something went wrong, developers deployed bad code, you restore your archives, turn the node back on, and there's perhaps just one table that you need to get restored to a point in time, specify that d-replayed list, and we will only replay that one table. Now, back in version 2.0, there was a change made to make level compaction strategy use the size-tiered compaction strategy when it got behind in level 0. So I think it was if there's more than 32 SS tables, use STCS. And there are some situations where that is not optimal. Typically, this is around bootstrapping. The use cases discussed in this ticket, Cassandra 6.6.2.1, if you're doing bootstrapping and you've got a lot of data and you're using LCS, just have a look at this ticket and see if it applies to you. It may be useful to start up with that parameter set. Now, lastly, is a neat little trick that came in version 2.0. There was an addition made to Java 1.7 early on that allows us to get around this horrible way that the JMX worked. So previously, we would advertise port 7199 as a JMX discovery port. When you connected, you would then reconnect back on some random port. And this was almost impossible to use in any real-life situation. This addition to Cassandra ENV ensures that all the traffic runs over port 7199, and you only have to have that one port open. So on to our old friend, YAML configuration. A lot of changes in here. Hinted handoff can now be enabled on a per data center basis. So the value that you can specify there is either true, false, or a list of data centers. You can also update this via JMX. So if you lose a data center, you've lost the WAN for whatever reason, And you don't want the nodes over in the West Coast constantly storing hints for things in the East Coast. You can update this YAML config, or more likely use the JMX and disable hints for it. Now, when these hints are disabled, they get tracked, and they get tracked against the same metric that we use if your node has been down for longer than the hint window. So you get an idea about how many hints you've dropped. Disk failure policy was added when all the work was done for JBOD, added a bunch of reliability in there, and we had ignore and best effort and stop. But stop didn't catch all of the cases. Sometimes when we read data off disk, we can actually get it off disk, but we can't make sense of it. So it may be a decompression error, it may be some sort of validation error, but we got it off disk, and those errors were turned into corrupt SS tables exceptions, and they weren't handled. Now, if you set the disk failure policy to stop, we will stop the node when there's a corrupt SS table exception. Stopping the node, of course, means we disable thrift, we disable binary transport, and then we disable gossip, leaving the process running, but effectively dead. It allows you to come along, look at the logs, and see what happened. There's also now a commit failure policy, just for the commit log. Now, previously, when there was an error writing to the commit log, it caused the commit log thread to fail, which caused your mutations to back up in the mutation queue, which caused all of your memory to get used, which caused garbage collection to go crazy, which eventually caused your node to go out of memory. If you want that existing behavior, change the default on this to be stop commit. If you'd rather have it, stop the server so that you can come along and sensibly see what's happening, leave it at the default stop. And when this happens, you'll get some sort of exception like this in the logs. It'll say, we couldn't write the disk because something was broken. If you've used LCS and it got a long way behind, like thousands of SS tables behind, you may have been bitten by the problem that Cassandra 5.661 fixes. So we have these file readers, and they have a 64 kilobyte buffer. And when we have compressed file readers, they have two, one for the compressed, one for the uncompressed. And a while ago, these were pooled and cached, and that made things go a little bit faster. But unfortunately, the implementation wasn't as robust as it could have been around aging those things out of the cache. So, or just controlling the total size. So if you have thousands of files, you will have thousands of these things cached, and that can take up space. So what happens now is those cached file readers are discarded if they haven't been used for about half a second. And more importantly, they're not added to the cache if the cache is above that setting that we saw before, which is going to default to 512 megs. So if you find yourself in a situation where you end up with thousands of files, Cassandra will now work a lot better. There we go. There are some defaults changed. And I'm just calling these out in case you've set these values yourself. And sometimes if you're using Chef, you kind of maybe take the default out of the YAML file and that ends up in your property bag and you never think about it again. Or sometimes the defaults change and it's handy to know that. So the number of threads we have that will flush an SS table to disk, controlled by the mem table flush writers. Previously, this defaulted to the number of data directories that you specified. And for most people, that's 1. That wasn't really the best way to stress the disks and get all the value out of these really fast disks. So now it's a value between 2 and 8, the smaller of the number of disks and the number of cores. And of course, if you're on SSD, you can turn that up. In the same way, the number of concurrent compactors. This used to default to be the number of cores, which was a bit too high. Now it defaults to be in a value between 2 and 8, again, based on the number of disks and the number of cores. This ticket fixes a bug that hopefully not many people had run into. If you somehow manage to send a thrift frame, a request with over 256 megs in it, there would just be an error on the server internally and you wouldn't get a response back. So now that property has been surfaced and you can see that in the YAML file. So it just improves existing behavior. It also kind of gives you a lever that if you've got some code out there that is hurting your machine and you cannot find it, you could turn this thing down a bit and then people will come and find you. And that's an easier way to solve problems. A couple of changes in the way that you can connect. For a long time, we've had the broadcast listen address. The idea there is that when we're listening for connections from other nodes, we listen on the listen address, and then we have the broadcast address. This is the one we advertise to them via gossip. Useful when there's network address translation in place. Broadcast RPC address adds the same functionality to the RPC system. That's the one that we advertise to clients when we're doing discovery via the new native binary transport, which I think now I should stop calling new. There's a little rule here that this can never be set to 0. If your RPC address is set to zeros, then that has to be set to one specific value. We can only have one value that we tell the other nodes to connect on. There's also a couple of new settings here as to how you specify RPC and listen that you want to connect to. Instead of using IP addresses, you can use the names of the interfaces. So this is going to simplify configuration. You know, a couple of less things that have to be different on every node is always good. Simple rule though, those interfaces can only have one IP address assigned to them. We've had this setting for a while called Tombstone debug threshold. And the idea of this was that when we're reading, we have to read all those tombstones off disk. We have to hold them in memory. If we're sending data over to the coordinator, we have to send them over the network. If there's lots of tombstones, it will hurt your garbage collection. Now this logged out a message, but you had to turn on the debug level logging on the slice query filter, and then the message itself just said, we read a lot of tombstones. Didn't tell you anything very useful. So that's been replaced. There's now tombstone warn threshold, which defaults to 1,000. When you do a read and it runs over 1,000, you get an awesome log message. Tells you the table, tells you the request, tells you all sorts of information. Together with that, there's a setting called tombstone failure threshold. So if a read goes over 100,000 tombstones, we will fail that. We will send back an invalid request exception, and that will give you time to go and think about the choices you've made. Meanwhile, we'll put this into the log, and we'll say, hey, there was an error, and we read 100,000 tombstones. Not as useful as that other, as the warning message, but the warning message will also be logged, I believe. And this is a quite small one, and I've just added it on here because a few people have asked about it. I've seen it around. This little setting, batch size warn threshold in kilobytes, if you send a batch and it is over 5 kilobytes in size, we log this little message. That 5 kilobytes is, I think, a little bit small. It represents a reasonable amount of text, but if you were storing some blobs or some chunks in the system, you're probably storing over that. It does, though, only apply when you do a batch, so it's not going to catch you if you're just doing single inserts. But if you see that in the logs, go back, change that setting, and you can get it out of there. Now, Jonathan touched on this one a little bit today, so it's probably not all that unknown now. Cassandra 6916 is magical, basically. It's awesome code. It replaces 3 settings that we had: compaction preheat key cache, preheat kernel page cache, and populate IO cache on flush, which was a table-based property, with 1. This one setting controls, this one setting is used to make it, as Jonathan was saying, a smooth transition from your reads against tables we're compacting onto reads of the result. So say we're compacting 4 100 meg files, we're making one 400 meg file, we want those reads to be nice and hot in between those two. So what it does is, as we're writing the new file, it preemptively opens up the portion of the SS table that we've written to the read path. It does that every 50 megabytes by default. So if you're doing a large compaction, there's quite a few 50 megabytes involved. And as that compaction's going, it will open it up, it will populate the key cache for elements for row keys that were in the key caches for the things we're compacting. They will get put into the key cache with the new positions in the compacted file. And it will preheat the I/O cache. And as it's going along, we will just seamlessly move to reading from a new file with a lot less reduction in our latency. For a while now, we've been able to set a throttle on the amount of network bandwidth we use for streaming. A happy Cassandra cluster is a balanced one. The idea of our Cedar architecture and all of this configuration is around making sure that all the different subsystems are balanced and that they can, one of them doesn't take resources that you want to use for a different one. And with streaming at a very low level, we go down to Java NIO and say, hey, can you take this data off disk and put it on that socket? We don't want that to go as fast as possible because that will saturate the network for the sending node. So we have a default stream throughput outbound of 200 megabits. Now there's an inter-DC streaming throughput. This is applied after the first throttle. So you can say, have a maximum of 200 megabits outbound for streaming, and of that use no more than 50 megabits for inter-DC traffic because my WAN is not really up to the challenge. A couple of little things in CQL3. Patrick, after lunch, is going to be talking about CQL3, so I'm not going to get too deep into that. There's alias support now. You can do select foo as total foo. Kind of useful if you're writing any sort of ORM out there. A lot of ORMs like to do ads for everything. There's an official way to disable compaction. Previously, we would set the max compaction throughput to be 0 and the min compaction throughput to be 0, and that would disable that for us. Now you can just say enabled equals false. And there is his new setting for compaction. Now, in version 1.2, the idea of Tombstone compactions was added. And it added a couple of settings to the compaction properties. Tombstone compaction interval, which said, hey, after 1 day, and Tombstone threshold, which said, after 1 day, if you have nothing else to compact, look at individual SS tables. If more than 20% of the cells in that SS table are tombstones that can be purged, run a compaction just on that one SS table and compact it into one other file and purge those tombstones out. Now, there are various reasons why we can't always purge tombstones. We cannot purge them when we think that the row is somewhere else, that we don't have all the fragments, because there might be a live cell sitting over in another SS table, and we purge off this tombstone, and suddenly your data comes back to life. There are some specific use cases talked about in this ticket, 6.5.6.3, where you may want to disable that check, and that is what that option does. So if you think that you're writing a lot of data with TTL, and it's not actually getting purged, have a look at that ticket, see if it applies to you, and do some tests. So we've got some new things to play with in the tooling. CQL.sh now has the ability to specify a SQL query on the command line. So that can be handy if you've got some scripting, some tooling around that. Previously, you had to pipe it in or something like that. It's just a little bit nicer. There are some nicer error messages in CQL.sh. This should help people who are new, and it helps people like me who keep forgetting because I started when it was Thrift. nodetool has had a complete rewrite. It is now a command-based structure. It's got a lot better help. It's got lots of new features on it. We've got one now where we can get and set the logging level. This is useful if you cannot change the config file on the node that you're dealing with. So rather than get angry and go and ask for sudo, just jump in and use this. There's information now about snapshots and how much actual space on disk they are using. nodetool lists snapshots, prints out a list of those, has the key space, the column family, and this idea of true size. So the size on disk is if you go over to that directory and do an ls, that's how much data is in there. The true size is how much disk you would get freed up when you delete that snapshot. And that true size as well also surfaces when you do nodetool CF stats. We now store a bunch of information about compaction. And this is stored in the system tables. System.compactions in progress for things that are running, and systems.compaction history for things that have run in the past. And this surfaces out when you do nodetool compaction history. There's an ID for each compaction task, the column family, how much bytes were in the original and how much in the output. I cut off one column here, which is the number of rows that actually got merged. So the merge count of, hey, there were 2,000 cells that only had one fragment and 5,000 cells that had two fragments. I don't know why, but the timestamp there, compacted that, is Unix epoch, which is not the most human-friendly thing. You can also now run repair at well, I was going to say a finer grain, but you could run it at sub-token ranges, so that's finer. But you can do some filtering. So you can say repair in this specific DC, or only in this DC, and the same for host. And so what this does is it goes and works out where the repair should run, and then filters it down. So this is useful if, again, your WAN link's not up to it, or you just know that one DC was down. Perhaps you dropped hints or something like that. It's very useful. Back in the old days, if you wanted to get level compaction strategy to rewrite all of your files, say, for example, you changed the min SS table size, you would just go and delete the manifest.json file. It was a bit of a hack, but it worked. Nowadays, the level that an SS table is in is stored in the SS table metadata, in the statistics.db file. So you can't do that. So there's a little utility called sstablelevelreset, and you have to actually, it won't work unless you put this really reset flag on there, because you probably don't want to do this unless you know what you're doing. For example, if you still had an old default for a size tier compaction strategy, you weren't using 160 megs or better for the min SS table size, you might want to rewrite all of your files. So let's look at some of the internal changes that have come through. Now, back in version 1.2, this ticket was added, and I missed it, but the comment was changed in 2.0, so when I was looking through the changes, I picked it up. So it kind of bends my rule a little bit about 2.0 and 2.1, but it's useful. If you have a wide partition in Cassandra, we store a row-level column index or a row-level cell index. And that chunks that wide partition up into 64 kilobyte chunks. Now, I did some testing on this way back in version 1.8, and it was pretty clear to see that in very wide rows, so tens of megabytes in size, different read queries had different performance, and that was mostly based on whether or not they had to read this row-level cell index. Reads that are just from the start of the partition don't have to, but if you've got any sort of offset in there or you're stepping into it, you do have to read them up. Now, the change in Cassandra 2.3.1.9 was to promote that row-level cell index into the key cache. It was already stored in the IndexedDB, so it's not a huge change for it to be there, but that really improves performance when you're reading from wide partitions. Later on today, Patrick, after lunch, in his data modeling course, is going to talk about this. And he's taken all of the metrics that I did back in version 0.8 and run them again in a CQL3 fashion against new Cassandra. And this really changes everything, makes the reads against wide partitions a lot better, which is good because CQL3 relies on that sort of stuff. You may or may not have known, but there was this big-ish lock in Cassandra called the switch lock. It was a reentrant read-write lock, and it was used to synchronize around the flush queue. Synchronize around the commit log when we're flushing the disk, sorry. And it's been removed in Cassandra 5.5.4.9. And so the memtable flush queue size was removed, and then the memtable cleanup threshold was added. The cleanup threshold describes the ratio between the total amount of data that you want, total amount of memory that you want to be allocated to memtables, and how much is in use. But removing the switch log makes life a lot easier. So as I said, it was synchronizing around the commit log. So what could happen is when we wanted to flush the disk, a thread would come along and it would take the right portion of the switch log. And if the memtable flush queue was full, it would sit there and wait for the queue to empty. And while it did that, any mutation threads that wanted to take the read portion of that reentrant lock would block. So while this was happening, your writes weren't making any progress. You would see this surface out in nodetool TP stats as all-time blocked flush writers. And there are a couple of data models that actually triggered this that I saw out in the wild. If you had a data model where you had maybe 1 or 2 tables that got most of the writes and 10 tables that got small writes, maybe they got a lot of writes, but they just didn't have as much data. So the memtable flusher would flush those 1 or 2 big ones all the time. Whenever there was something to do, it would flush those down. And whenever we ran out of space in the commit log, we would flush out a segment of the commit log, and then we'd try to flush 10 memtables at the same time. And that would fill the queue. Now, it may not fill it for very long, but it would. And you'd see blocked flush writers going up. And the way you worked around this was you increased the number of memtable flush writers, you increased the queue of the memtable flush. You don't want that to get too big because that's stuff that's building up in memory. Or there's the setting now for being able to flush on a time basis per table. But basically, it was a problem you'd run into, and latency would spike. And also, the switched lock, the reentrant read-write lock, was not the fastest thing. So there was a lot of engineering done to remove this, and it makes our write path a lot faster. And if you are seeing blocked flush writers, try changing some of those configuration settings I mentioned, and when you get to 2.0, it'll be gone. Cassandra 5.202 makes a small tweak to our on-disk layout. It adds something to the column family name. It adds this unique ID to the column family name on disk. This only happens to column families that are newly created, but it is going to make your life just a little bit more interesting if you have any scripting that touches disk for looking at things looking at the actual data files on disk. As Jonathan mentioned, I should have checked with him, but you can specify how many rows, how many cells to put in the cache. For the row cache, that makes the row cache a little bit more useful. There's a change to what happens when you specify join ring equals false. So that's one of those that's one of those Java JVM parameters, -d Cassandra dot join ring equals false. The server will start up when you start it, but it won't join the ring. It'll just sit there, and it won't get any reads or writes. Now, imagine you had a node that went down, and it went down for longer than the hinted handoff window, and you then wanted to bring it back up. So you bring it back up, you have to do a repair because the hints weren't stored for it. And there was a time when you brought it up, and if it had to join the ring so it could run repair, so it could talk to the other nodes, it would be serving stale data for reads until the repair had completed. Now that may be okay at CL quorum, but you're going to get a lot of digest mismatches potentially, and those reads have to run a second time, and you'll see a lot of blocking read repair happen. If you're using CL1, that's a bit of a pain because now you're getting a lot of stale data coming out. So if you start with join ring equals false now, it will enter hibernation mode, in which case it's part of the ring, it receives writes, but it's not going to get any reads. So you're not going to serve any stale data. Once you've started the node up, then you do a nodetool join, and you're back. This one might be handy if you use snapshots as part of a backup system. We now create a little JSON file, and it lists all the files that are part of the snapshot, can make all the SS tables that are part of the snapshot, and make your life a little bit easier, perhaps. Now, this ticket is really nice. It makes it a lot easier, a lot more efficient for us to do things like time series selects. If you create a table that looks like this, and if you've seen this, I just stole this from Patrick McFadden's talk, and then you do a query that looks like this. So we say select blah, 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 where event time is greater than this and less than that. We now track these the event time column values. These are clustering keys. Remember, weather station's the partition key, event time is the clustering key. We track the min and max values of those per SS table. And when we process a query like this, it allows us to skip out whole SS tables because we know that they are not going to contain any values that are within the range that you specified. And so if you've got time series data and you're running with this, it'll be a lot faster. And that's the end of my talk. I think the takeaways here are that 2.0 is awesome and 2.1 is even more awesome. You should get on to 2.0 if you're not on it, and you should get testing on 2.1. My laptop on 2.1, just a MacBook Pro, does 60,000 writes a second, and I find it really hard to make it do garbage collection in a bad way. So thanks for that. I think I've got 5 minutes for any questions if you have any. No questions? Thanks. Have a good day.